Alright folks, next we are going to look at section 5, bond energy and enthalpy change of atomization. Right, we have a definition of bond energy over here. So it's the energy required to break one mole of covalent bond in the gaseous states. Right, so this is the textbook definition, or what we give you in the notes, that is sufficient for H2 Chem. But if you want to be a little bit more explicit or a little bit clearer, then we have to highlight that the bond energy is the energy required to homolytically break or overcome one mole of covalent bonds. So this is very specific. We are referring to homolytic bond breakage. Okay, so what is the difference? So maybe I'll highlight a little bit of difference over here. So for example, if we have hydrogens, okay, so we have hydrogen gas over here, right? If we break the covalent bonds homolytically, what's the meaning of homolytically? So that means that if you draw the dot and cross, okay, so there is electrons, they are sharing one electron or a pair of electrons, right? So if it undergoes homolytic bond breakage, you are going to end up with two gaseous hydrogen atoms. Yeah, so this is quite clear. Homolytic bond breakage. Okay, now there is another kind of bond breaking known as heterolytic bond breaking. Okay, so I'm going to spell it out here: homolytic and heterolytic. Okay, now if you break them off heterolytically, right, you're going to end up with a gaseous H plus cation and a gaseous H minus N ions. Okay, so that actually involved, okay, the first ionization energy of H, so you get a H plus gaseous, okay, plus electrons, and then plus the remaining H atom, okay, and then an electron affinity over here. So that's the difference. So for heterolytic breakage, it involves three terms. Okay, so this is bond energy, right? This is first IE, okay, and this is electron affinity. Right, so if you are very strict with definition, then you have to be very clear that bond energy is the energy required to homolytically break one mole of covalent bond in the gaseous state. Yeah, but of course for H2 wise, not too much of a concern, because in most cases we are sure that, or it's assumed that when you talk about bond energy, you know that you are going to end up with the gaseous atoms. So there isn't a need to go into the specifics. Yeah, so I thought I just want to make mention this. I mean, in the event that you're going to end up with some questions that are quite interesting, then at least you know how to handle them. Yep, by virtue of the definition. Okay, so every bond energy term you see in the data booklets, yeah, so they refer to homolytic bond breakage, because that is the definition. Okay, in case you do not know the existence of the bond energy data in your data booklet, maybe let me point you towards section 3 of your data booklet. Okay, so there are two sections, if I'm not wrong. So there's 3A, and 3A's are for diatomic molecules where the values are exact. Okay, why are they exact? Because these are the only there's only one HH bond. There isn't like non-exact HH bond, unless of course the hydrogen atom is, the hydrogen molecule is interacting with the metal surface, and that causes the HH bond to weaken. Other than that, these are exact values. Yeah, so these are not average values. Same as diatomics like HF, HCl, etc. Okay, and of course, carbon monoxide, we have to make mention here. It's the strongest bond ever known to mankind. Okay, 1,077 kilojoules per mole, even stronger than nitrogen triple bonds. And why is that the case? Yeah, its bond strength is enhanced by the partial ionic character. So in most cases, that's how we describe it. 3B are average values because they are just so many compounds with CC, CH, CF, etc. Yeah, so these are average values that we taken from a large sample of compounds, and then we just compound and average up. Yeah, so the actual bond energy of a specified compound may not be close to these values. There could be other reasons that leads to the strengthening or weakening of the bonds. And if you are being asked in exam, then you need to look at the factors that affects the bond strength. Okay, so you have quite a bit of them. You just need to know where to look out for these data. Okay, some of the data are not available, so you need to know. I mean, it will be to your advantage if you know where to find the bond energy data. Okay, yep. Then we come back to energetics. Okay, so they highlighted some of these things, like for example, bond energy must be positive because bond breaking is endothermic. You need to take in energy to overcome the electrostatic forces of attractions between the atoms. Okay, so I think this is clear. So do you need to write the positive sign in front? I mean, if you can remember, you can write. If not, then I think it's understood. Okay, so you have to be clear whether you're talking about average bond energy or actual bond energies. Yep. Okay, then 5.2, we are looking at calculation involving bond energies. Okay, so in general, of course, a real chemical reaction probably doesn't work this way. Yeah. So normally what we are looking at is we want to look at what happens when when all the covalent bonds in the reactants are broken to give you the gaseous atoms. Yeah. And then what happens when the covalent bonds in the products are overcome to give you the gaseous atoms. Okay, so this is what it means when you have the summation. So normally when you draw the arrows, normally it will be in this particular direction because you are looking at bond breaking. So this will not be a minus bond energy. It will in fact be a positive bond energy. Yeah. So when you do the summation, you're going to take all the values here and then minus these values. The reason is because bond breaking is endo, but bond forming is exo. Yeah, so you have to be a bit clear in what you're doing. Okay, other than that, if you follow this, you'll be fine. But you need to know the reasoning behind that, and that's why I was just trying to explain to you why is it that whenever I draw a cycle, I will not put the arrow in this direction and put a minus. Instead, I will put in this direction and I will leave them as the bond energy data. Yeah, but it's really up to your preference. Doesn't really matter. Okay. Yep. So there will always be some discrepancies because there are a few reasons. Normally, one of the reasons is because the values in the data booklet are cited as average values. Yeah. So the actual values is influenced by the chemical environment around the atoms bonded to each other. Okay, or it could be because this particular molecule is interacting strongly with some other molecules, and that might cause the weakening of the bonds. Okay, or maybe in catalysis environments, for example, in the Haber process, you learn that in secondary school, nitrogen and hydrogen comes together on the metal surface, and that leads to the weakening of the N and the HH bond. Okay, and sometimes the discrepancy is due to the fact that the molecules, the reactants, and the products in question, they are not in the gaseous phase. Okay, so they are actually in the liquid or solid phase. So that's why when you use the bond energy to perform any energetics calculation, you notice that the enthalpy change calculated will differ quite a bit from the actual experimental values. Yeah, because perhaps you're dealing with liquids instead of gas. Yeah, so normally when they ask you for the reasoning, you can either say that these are average values, or you can say that the enthalpy change of vaporization or whatsoever is not taken into consideration in the calculations. Okay, I think they are listed down in your notes. Okay, yeah, so next we look at exercise 5.1. So work examples here. So I will just briefly mention what has been written. So you have oxyacetylene torches, okay, operates at 3,300 degrees Celsius, fueled by acetylene. Okay, so this is the reaction. Then they ask you to use bond energy values from the data booklet to calculate the enthalpy change of reaction. okay, of the above reaction. Okay. So what happened is that you might want to draw a cycle if you wish to. So okay, a cycle is not drawn here, but I mean there are some values being written here, but what I can do is I can complete the loop by drawing a cycle. So I'm going to draw an arrow down. Okay, so I'm going to calculate how many bonds are broken here. So it's written out for you. So you have 4 CH bonds, 2 CC triple bond, and 5 OO double bond. Okay, so I'm going to end up with 4 gaseous carbon atom plus 4 gaseous hydrogen atom plus 10 gaseous oxygen atom. Okay, normally I like to draw like this, and then I will also arrow down. Yeah, so that is why when you perform the calculation, you're gonna end up with summation of this value minus this. Yeah, that's the reason, because I'm going opposite the direction of the flow of the arrows. Okay, so you get 5,800 minus 8280, you get negative 2480 kilojoules per mole. So that's a lot of heat released, and that's why you can see that the temperature can go as high as 300 degrees Celsius. Okay, so you have a comment here. So they mentioned that to help visualize, it's good to draw the full structure formula. Yeah, so that's the reason why it's being drawn for you. You guys might not be familiar with the naming, organic chemistry naming, like you don't know what is acetylene or ethyne. It doesn't matter at this stage. When there's a need to, we will give it to you, the structural formula. So we will not disadvantage you when you're doing questions before you learn organic chemistry. Yeah. So they ask you to calculate another value for the enthalpy change of reaction for this reaction, okay, using the following enthalpy change. Okay, so you're given the formation of acetylene, you're given the formation of CO2, you're given the formation of water. So it's the same thing. You're operating using the formulas shown to you in the earlier parts. I think it's over here. Summation of formation of product minus reactant. But if you recall, I usually don't like the students to use this, so I would rather that they define the terms as it is. Okay, so in that case, what I'll do is I'm going to write this out: C2H2 gas plus 5O2 gas. So this is 2 here, then arrow 4CO2 gas plus 2H2O gas. Okay, so the formation of this will be 4C solids plus 2H2 gas plus 5O2 gas. Okay, so this is the formation. I'm going to write down, this will be the enthalpy change of formation of acetylene. So 2 times enthalpy change of formation of acetylene. And then for oxygen will be 0. And then this will be 4 times enthalpy change of formation of CO2 and 2 times enthalpy change of formation of H2O gas. Okay, so make sure that it's gas that you are writing and not liquids. Okay, so that's why you have summation of this minus that. Yeah, okay, so you get negative 2514 kilojoules per mole. Okay, so enthalpy change of formation of oxygen is 0. If you wish, you can highlight this. Okay, so this is 0. Other than that, you don't have to talk about it. I mean, in most cases, if you already experience, you might not even need to share with the audience or write in the exam paper that is 0. Okay, then they ask you to suggest a difference for the values. So the reasoning given here is, of course, looking at average values. Okay, so it may not refer to specific bonds, because specific bonds may be stronger or weaker. Yeah, so we are looking at perhaps the difference between the values is about 30 kilojoules per mole. Okay, not too huge, not too bad. Okay, yeah. So we'll move on to exercise 5.2. Then we'll see how the discussion can take us forward. Okay, so we have sulfur hexafluoride. It can be made by reacting sulfur tetrafluoride with fluorine. Okay, then they ask you to consider the bond and broken and bond form. Calculate a value for the average mole energy of SF. Okay, so state any assumption. Here, of course, the assumption I need to state, I hope it's obvious enough, might not be too obvious, that the SF bond strength in SF4 and SF6 are the same. You have to state this assumption, if not you can't calculate. Okay, so I will attempt to draw SF4. Sulfur is in group 16, so it has 6 valence electrons, 4 of which are utilized to form single bond with fluorine. So you're left with 2, and that will be the lone pair. So with that, then you can easily draw the structure of SF4 out. Yeah, so it will take on a seesaw shape. Yeah, so again, good to draw the structure out so that you roughly know how many bonds are broken or formed. So plus F, okay, gassed, and then I'm going to get sulfur tetra hexafluoride. So S, F, 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 F. Okay, yep, then this is gassed. Okay, so this is given to be negative 434 kilojoules per mole. If I try to break all the bonds here, if I let the average SF bond be bx, so this will be 4x. Okay, then I'll flip over my data booklet. FF bond energy is 158. Okay, so with that, I'm going to get sulfur gas plus 6F gas. Okay, and then in this direction, it will be 6x. Right, so now we can solve it. Okay, so that will be, we're going this direction. So 158 plus 4x minus 6x. Okay, is equals to negative 434. Okay, then I'm going to solve for x. So 2x is equals to a certain value. Then x will be equals to, let me punch the calculators. 434. Okay, I'm going to end up with positive 296 kilojoules per mole. Okay, yep. Okay, so assumption I've already highlighted. We assume that the SF bond strength for SF bond strength for SF4 and SF6 are the same. Yeah, but this is far from the truth. They are not the same. In fact, they are quite different. Yeah, so why are they different? You learn more in university when you encounter molecular orbital theory, because that will help you to firm up your understanding. Okay, right. So we're going to move on to the next part. Enthalpy change of atomization. Okay, so is the energy required one more gaseous atoms to be formed from the elements? Okay, under 200 Kelvin, 1 bar. Yep, so if you flip over your data booklet, okay, let's say for bromine, right? You might notice something interesting, especially for hydrogen. Okay, so if I flip over, for hydrogen, right, you notice that it's 436, right? Half of 436 is about 218. It's 218 actually. So is it true that therefore for diatomics, enthalpy change of atomization is half of the bond energy? Well, I mean, it need not always be the case. Okay, let me check. Okay, you see, for example, bromine is 193, right? Yeah, but atomizing to form one mole of bromine atom is not half of 193. Why? Yeah, because number one is bromine at standard condition is liquid, it's not a gas. So you still need to incorporate more energy to vaporize it before you homolytically break the covalent bond. Yeah, so it's not always half unless you are talking about gaseous molecules. Okay, to begin with. Yeah. Okay, what are some elements with enthalpy change atomization 0? So that is something for you to think about. Okay, any elements with enthalpy change of atomization 0? Okay. Yeah, so there's a difference between element and compound. Yeah, so for compound, is the energy required to convert one more of it into gaseous atoms. Yeah, so for the case of CH4, right, you're going to break all the 4 CH covalent bond, and you're going to end up with an enthalpy change of atomization for this compound, 1662. Okay, so here you were told that it's always positive and it always involve breaking bonds. Okay, I think this should be quite straightforward. Okay, then yeah, so for this part, for gaseous molecules, so this is for gaseous diatomics, okay, uh, there's a relationship between bond energy and atomization enthalpy. Yeah, so atomization enthalpy is always half of bond energy. Yeah, but this is the only case lah. For other cases, if you are given the data, then you should use the data. If not, then you could use this as a proxy. So for example, for bromine, if you're not given the enthalpy change of vaporization, then you can use half the bond energy of BR as a proxy. But this is a bad proxy lah, because you know that enthalpy change of vaporization is not taken into consideration, so it might be underestimated. Alright, so end of section 5, we have exercise 5.3 for us to work on. So phosphorus exists as P4, and then they ask you to use the following data to calculate the average bond energy of PP. So you are given the standard enthalpy change of formation for P4 gas, okay, to be 58.91 kilojoules per mole, and enthalpy atomization for phosphorus is 314.4. Okay, so let us try to link up the data. The reason why they drew this for you is for you to calculate how many covalent bonds do you need to overcome. So 6 pp bonds you need to overcome it. Okay, so let us try. So first of all, okay, exists a molecule. Okay, so I have P4 gas. Okay, I break all the bonds. So if I let it be X, so we have 6X here. Okay, then I'll get 4P gaseous. Okay, so this is the gaseous molecule. Okay, then enthalpy change of formation for P4 gas is defined as the enthalpy change when 1 mole of P4 gas is formed from its constituent elements. The constituent element, it should be a solid here. Okay, so this is given to be 58.91 kilojoules per mole. Okay, then you were also told the standard enthalpy change of atomization for phosphorus. So the definition based on the top is for one phosphorus atom to be formed, the standard structure of phosphorus needs to take in 314.4 kilojoules of energy. So now I'm forming 4 phosphorus atoms. So therefore, I will need to take in 4 times 314.4 kilojoules of energy. Okay, so with that, the calculation should be straightforward. Okay, so from here, we're going to go from anti-clockwise direction. So that would be 6x equals to 58.91. Okay, it's minus because it's reversing the direction of the arrows. Okay, then plus 314.4 times 4. Okay, then I solve for x. Okay, so I should be getting about 200 kilojoules per mole. It's a relatively weak bond. Yeah, so that could be a follow-up question. Why is, or I mean, they might say something like, oh, this PP covalent bond is weaker than usual. Just curious if PP is given here. Let me check. PP. Oh, PP is not given. Yeah, so you can do a check. It's weaker than usual. Then usually they ask you why. You notice that the phosphorus here has 4 electron groups, 1 lone pair and 3 bonding electron pairs. Right? Usually for 4 electron groups, we are talking about a tetrahedral geometry. Then now you notice that it's confined into a pyramid. Yeah, so because it's forced to confine into this environment, maybe there might be significant bond-pair repulsion. So usually in a strained system like this, right, when they're constrained into a certain shape, yeah, the bond-pair repulsion will become more significant because number one, you force them to take on a certain angle. Number two, you force them to be close to each other. Yeah, so because of that, the repulsion will weaken the PP bond. Yeah, so if there is a follow-up question, and usually you get that in exams, they will tend to ask you, oh, why is the bond weaker than usual? or maybe they give you two scenarios. One is the not constrained one, the other one is the constrained ones. Then with that, you should be able to give a credible answer, based on the data provided.